Hello, everyone. Welcome. Thanks for joining our diagnostic training session today. And what you're about to see is a pre-recorded training session we did over in the United States. But be assured that a lot of the material that we cover is really applicable to any automotive application. So just be aware that yes, it is a lot of North American vehicles, but they will apply a lot of the same principles apply over in the UK as well. Now, if you do have any questions, if you're watching this during the premiere, you can just leave it in the chat. We'll be monitoring live chat. If you're watching this after the premiere, then just feel free to leave a comment underneath the video and we'll get to those as we can as well. So my name is Jason Gabrenas. I'm one of Snap-on's diagnostic technical trainers. I've been in the training department since 2013, traveling around North America, helping techs and shop owners get the most out of their diagnostic equipment. Before I did that, it was a couple years as a diagnostic sales rep at Snap-on, so I had 30 different franchisees I worked with, as well as the shops that they serviced, in order to help everyone get the most out of their diagnostic needs. Then before I did that, it was 8 years at Subaru. So I worked in a dealership, and over time, I guess, just became the default diag guy in the shop. So I always ended up having the drivability problems, the intermittent problems, the weird wiring problems that would show up on those cars. And that's really where I cut my diagnostic teeth, was trying to figure out all those weird head scratcher type cars that would come into my bed. Then before that, a bunch of other miscellaneous wrenching jobs. Been a little over 25 years under hood experience for me. So our topic today is component testing, electronic throttle control, and this is part 2 of 2. If you were with me last time, we had part 1, and this will be a continuation, of course, with part 2. So we talked about last time with electronic throttle controls, how we took away the cable on the system. So now we have two different sides. We have our accelerator pedal, not a gas pedal, but an accelerator pedal with an accelerator pedal position sensor, which then sends a signal to the PCM. The PCM makes a calculation based on load and speed and throttle input, and then sends an output control to the throttle body, which then opens the throttle plate. Now, this is all inside mechanical gears, and we'll actually see a couple pictures of that in a little bit. And then also, didn't draw it on this picture, but feeding back to the PCM is the throttle position sensor. So the PCM can open the throttle and then know where that throttle is open to based on its output, right? But if we think about it, we now have two different sides to our throttle. We have an input side and we have an output side. So the input side is going to be whatever you are sending to the computer. So in this case is the accelerator pedal position signal. It's going to send it to the computer, and that is telling the computer, hey, I want the throttle to be open this far, right? And then the PCM, whatever it decides, it makes a calculation to open that throttle and give you the proper response that you need. And of course, it all happens in fractions of a second, because we really nowadays, maybe the early ones weren't as good, but nowadays on most of these modern systems, it's like almost instant feedback as soon as you hit it. But, and this is a but, we're going to see this a little bit later when we look at some of the scope patterns we captured. It doesn't always react evenly or proportionally to how the throttle is because of how the load is on the engine. So we'll see that in a little bit. And also because of this, the PCM can control the throttle body independently of whatever you're deciding that you want to do with the throttle. For example, if you have a bad throttle or bad accelerator pedal position signal, it can still open the throttle a little bit to at least give you a limp mode, but well, you can press the pedal all you want, it's not going to work when it goes into a limp mode like that. Or it just depends on maybe cruise control, right? If you use cruise control on any of these vehicles, the computer doesn't really even care what the accelerator pedal is doing because your foot's off it usually anyways. So it's not needing that input unless you feel like you want to accelerate the vehicle. Then it would see the input and act accordingly. But it can control the vehicle speed, no problem, just by controlling that output side, just by controlling the throttle. So if we think about the accelerator sensor and the throttle position sensor, on many of these vehicles, it's just a simple potentiometer. It's a 3-wire system on the older systems, where 5 volts go in. We get ground coming out the other side, and we have this, it's like a coated wire, right? So it's a conductive surface, a coated conductive surface with variable resistance. Depending on where this arm goes, this wiping arm wipes over it, and it will send a signal back to the PCM at a different voltage depending on where it is. So if it's sweep back and forth, it'll sweep back and forth, and it'll send a varying voltage out. So if we remember from last time, we see the voltage comes in, and then how this would look on a scope is voltage comes in, we sweep it up. When we get to maximum, it'll level off because that's as far as it'll go. That's the maximum voltage output. And also note, when it's closed or when the throttle's closed and the key is on, we should still have some voltage because it's going to be open that little tiny bit just to keep the vehicle idling if it needs to or what have you. So you usually get about half a volt, 0.4 of a volt I've seen. All right, so it starts at a low voltage, goes up to usually most vehicles is 4.5, 5 volts. Just depends on how the manufacturer decided they wanted to design it. And then when we go and close the throttle, once again, it comes back down the other side, goes back to that half a volt or so. So this is on a traditional throttle position sensor. Now, newer styles on these electronic throttle controls, well, they have a backup, as they need a backup. Just in case one side fails or one sensor fails, it needs another sensor as a backup. So if we look here, this is the surface that these wiping arms, there's the two contacts there and the two contacts there. They wipe over this, and depending on the resistance between the two, we get the different voltage. So we got one sensor track there, one sensor track there. So that gives us a dual sensor. All right, so we have a dual throttle position sensor, and we have a dual accelerator pedal position sensor. That way it gives us that that backup there. So it's the same thing, it just swipes back and forth. It's a potentiometer, but we have two outputs to the PCM. Generally, they'll share a common 5 volt and a common ground. Maybe they have individual 5 volts and grounds. It depends on how the manufacturer decided they want to wire. All right, so oftentimes it is a 6-wire sensor. So yeah, I guess it does have 5 volts and ground on both. 5 volt signal and ground on both. But how it would look if I were to look at both signals at the same time, we'll see that depends on the vehicle. Some vehicles it will be they'll be the same. Some vehicles they'll be a certain amount apart. Some vehicles there'll be like a logarithmic difference between the voltages. So in this case, on this vehicle, they're separated a little bit by about 3/4 of a volt on this case. And then you sweep it up, it goes up, and then you see how they get closer together at the top. So this is like a this one goes at sort of like a logarithmic voltage difference, and then it comes back down. Right, so we can see the difference there, how it goes up, comes down. So that's the one that's different. So this is very, as far as I can tell, this is pretty uncommon in the automotive world out there to have them with such a difference there. And then when it goes up, it gets close, and then it gets closer here, kind of like a logarithmic, as I said, difference. This is on a Subaru. Right? Subaru is really the only one I've heard of that has this. I'm sure there's probably other manufacturers out there that do it this way, but Subaru is kind of a weird duck anyways. So I wouldn't be surprised if they're the only ones that use that type of logic with it. But that makes it so if we have different voltages, we can still tell, is there one sensor working? Is the other sensor working? Fairly common out there is going to be just two voltages paralleling each other. So one will be at, in this case, 1.25 volts. This was at 1.75 volts, and they just stay that half a volt apart the whole time, and they mirror each other. That one's pretty common. And then another pretty common design that I've seen out there is one will start high and then go low at full throttle, and then one will start low and go high at full throttle. So they kind of meet in the middle. When you're at about half throttle, they're at about halfway in between. So one goes high and one goes low. So that's fairly common too. I've seen that out in quite a few vehicles. This one's off a Hyundai. I know I've seen it on BMW. That one's kind of common too. So the two most common patterns you would see is a parallel voltage and then the crossing voltage, where one starts high, goes low, one starts low, goes high. If I'm testing it, that's what I want to look for. So the two main input and output pieces to our electronic throttle control is going to be, of course, our accelerator pedal position sensor, which we talked about last time. It's usually a six wire connector, so I have 5 volts in, power, ground. And then the same with the electronic throttle control. In this case, it's a 6-wire as well, but there's a reason there's 6 wires on this one. All right, so throttle position sensor in this case is 4 wires. We'll see that right here. All right, so here's my 6-wire accelerator pedal position sensor. So I have my number 1 and my number 2. We got power in, we got ground, and then we got signal. on the throttle motor assembly or the throttle body assembly, we have a common power, we have a common ground, and then we'll have a signal that goes out from each sensor. So we have dual sensors right here. This is on a Toyota. So we got power goes in, and then we got ground over here, common ground, and then we have our signal wires right there that go out. Right, so we can see those two right there, and it'll send the different signals, right? And then if we want to look at the pin assignment, we see that we have electronic throttle motor minus and positive. We'll talk more about that in a second. Sensor ground, subsensor signal, throttle, 5-volt reference, and a main sensor signal. So as we said, we have a main sensor and a subsensor, power and ground. And then the motor itself. The motor itself, if we've taken one apart, well, there's a throttle position sensor on it. Right, so we can see where the tracks are on this particular vehicle. We can see how it's kind of on the back side there. And then there's a connector, and there's a traditional throttle position sensor. On many of the newer designs, you also get a Hall effect sensor, which is better, I guess, mechanically wise, is better, because now we don't have a mechanical failure point. We don't have contact. We don't have friction. If we think about that potentiometer on that throttle position sensor, if I'm just driving down the road, that little wiping arm is going to stay in the same spot as long as my throttle's staying in about the same spot all the time. So over time, it can wear, and it can wear off that little wiping spot. In a Hall effect design, you're not going to see that, right? It uses magnetism, and it sends out a signal based on where the magnetic field is in relation to the sensors. So that is better, I guess, as a wear item. Now, maybe a little more expensive, I suppose, but it's better as a wear item. Now, if we look closely at this, I have an exploded view on the next slide, but our motor is here, right? So it is a DC motor, and it's a servo motor. So depending on how the computer tells it to open, it uses a pulse width modulated signal. So it turns it on and it holds it open at a certain range. And then the springs also help as well. There's a both-way spring, and it'll hold it open to a certain point. We have a gear here that rides off of that, and then we also have a reduction gear there that will ride on this back and forth type cam type of a gear there, and that will be attached to the throttle plate. Throttle plate goes through here, or at least the rod does, and then it turns it back and forth. Common failures on this at that point, since we don't really have much of a failure point on our Hall effect, common failure I've seen as well could be the gears. All right, over time the gears wear out. That can give you a slow throttle response. It still might open, but the gears can wear out because they're just plastic. So over time, depending on how often it's used, the gears could wear out in there as well. So I've seen that before. So if we wanted to look at that exploded view, there's our throttle plate. All right, and it goes to this the shaft here, right? We have the shaft, which has on the other end will be that Hall effect switch. Got the gear that rides on this, and then also rides on the electric motor. There's a little spring in there to keep the motor where it needs to be. We got double springs for both open and close. It's got a bearing, idle screw, gasket. There's the actual cylinder bore right there. There's a cover, and the cover also has the sensor built into it as well to read off that Hall effect switch, right? So that's everything that's in that side. It's going to be mainly gears and that throttle position sensor that's in there as well, right? So main failure points in there could be the motor, it could fail, and then the gears could fail, right? A mechanical failure, and then also the throttle position sensor could fail. Right, so a lot going on inside there. Seems a little more complex than it needs to be. Also makes it way more expensive than it ever used to be as well. With the older, simple, just open and close throttle bodies without the electric motor or anything, they're way cheaper. All right, but now we have this whole motor assembly and everything, and price goes up a little bit more. But it's really interesting to me watching this work. So what we did is we hooked up to a scope and took a couple different patterns depending on what we had going on with the vehicle. So in this case, this is going to be a brake torque on a vehicle. So the yellow is going to be the accelerator pedal position sensor. The red is the throttle position sensor. All right, so here's my input, the yellow. here's the pedal. And then on the output, here's my throttle plate, my throttle position sensor. And this is with an engine torque. So in drive, match the brake, match the gas, get it to torque up real good, give it a good load. You'll notice here, right about here is where the accelerator pedal started. And right about here is where the throttle plate started moving. So you see there is a little bit of a lag there. In this case, it was 23 milliseconds of a lag between when that started and when that opened. You'll also notice at the time when that opened, that's when my pulse width modulation began on the throttle motor. So these green lines are the positive signal on the throttle motor. And then the blue lines are the negative signal on the throttle motor. So that is commanding it backwards the other way, back to close. All right, so we got open command, and then it holds it open. And then we have a close command when the accelerator pedal goes down, and then we have the close command there. So that's kind of cool. You can see the open, you can see the close, you can see the accelerator, and then you can see the throttle response with it as well. Here's another one that I thought was kind of interesting. So this is without the engine running. So this is key on, engine off. And this is a whole zoomed out view of just some sample patterns we were trying to do. So this is key off, and then key on, you'll see the voltage changes. So on my throttle position sensor, we have the voltage going up there. And then also the accelerator pedal, the voltage comes up to a little over 0.5 volt at the same time. So we have that there. And then this is just a little throttle check. So it sweeps the throttle open and close real quick. But maybe a couple seconds after the key is on. So we wait for that to happen. And then as soon as we started opening the accelerator, now notice we open the accelerator, press on the accelerator pedal, give it a nice smooth up to full throttle. That throttle plate didn't move much. Accelerator started, throttle plate open, few percent, maybe 20%, something like that, with no load on the engine. And then all of a sudden, when it gets to a certain amount of throttle input, I don't know, maybe 80%, something like that, it just goes poof, all the way to full open. You can actually hear it in the car if you press down on the gas. I said I'm not supposed to say that. And the accelerator pedal, you press down on the accelerator pedal slowly. You can hear it when you get to about maybe 80%, it goes click, and that's the throttle plate snapping wide open. Since there's no load on the engine, that's what we're seeing right here. So it's no load on the engine. It doesn't really need to open until it gets to, a full throttle command, then it opens wide open. And the same thing on the way down, it closes partially and then it closes fully. And then over here are a bunch of wide open throttle blips that it did really quick. Just instead of a gradual roll into it, we did really quick blips right there as well. All right, and then there is the key on, engine off. That's zoomed in a little bit closer on that wide open throttle sweep, so we can see how it came up and came down like that. And then we can see our openings. Not a lot of negative voltage there, more of the positive voltage there to move it around. So it just depends on where it was at. All right, and then we have the, this is a driving test. This one was kind of interesting too. So this is kind of driving on down the road, and then at a stoplight or stop sign, and then started taking off from the stop sign. You can see the throttle input goes, or the accelerator pedal input goes up, throttle pedal input goes up, and then it increases and goes up to here. You'll notice that the accelerator pedal is not all the way open until over here. And then the throttle plate just kind of levels off right here as well. This point, it went pretty quickly to full throttle, right? So that's actually where the vehicle shifted. So it went, shifted, and then it actually opened to full throttle. And then as soon as we let off the throttle, you can see all this activity here with the positive and the negative, trying to get that throttle back down after the shift. Right. So I thought that was just kind of an interesting look to the pattern where we had this big spike right at the end, right where the shift point was. So I thought that was kind of interesting. So let's take a little bit more of a look at these patterns. We can look at a few more in there. Boy, there's a whole lot going on in my YouTube chat right now. I'm not 100% sure what's going on there, but hold on a second. Let me just take a look here. I got a lot of people on. Timeout. I'm going to put you guys in timeout. I don't know why in the world that's happening. They're deleting their messages or chatting. All right. You're out for a little while. Okay. 5-minute timeout. Okay. All right, let's take a look at the scanner here and take a look where we would see some information, right? So we have vehicle history and got a couple of different things. So this is the this key on engine off. Let's talk about that one first. So I'm going to open this up and I'll zoom out so I can see what's going on here. There's that looks exactly like we saw in the picture, right? Because that's the fully zoomed out image. If I wanted to come in here a little bit closer, we can see what's going on with our, it's probably a little tight, but we can see where it comes up. Accelerator pedal comes up, and then we can see our pulse width modulation. You can see the different sizes of square waves where it modulates that motor to keep it open or to open it up in general. Let me go back out and we'll go over to maybe this guy right here. So this is a wide open throttle snap. You should be able to see that pretty good. Yep. So you can see where it snaps throttle and then the throttle opens with it accordingly since it didn't have a low, but you can see how after it really took a while to come back down to trail. Let me turn on my cursors and see how long that took. So as soon as we went from full throttle to closed, it took, doesn't look like a ton of time. It took 0.04 seconds to react, right? So that's not very long. But you can see it did take a little bit of time to react. Let's look at this one over here. Go to throttle fully closed. Where's my throttle sensors? Let's go. All right, so you can see 0.04 seconds there again. And when we went to open, to where the throttle opens, that's 0.05 seconds. It could be 0.04 seconds. I didn't exactly put them in the best place, right? So we can see that how it opens versus how it closes. And this is key on engine off, right? No load on the engine, no calculation of load. So we don't really need to worry about we saw how it did some weird things, right? Let's see. So this is loaded in part or in drive, right? So we can see the different load cycles here. So let's zoom in on this one right there. Goodness gracious. All right, so let's go here. All right, so this is loaded. So this is in drive doing a brake torque. So throttle opens here. We can see that the accelerator opens here, throttle plate opens there. And then they do follow each other pretty well right along until it drops off over there as well. And you can see how it opens right here, leaves it at wide open throttle. And then you can see how it has some more activity there. And then when it closes, we have that negative signal there as well. So we have a positive and a negative signal on that sensor. So I thought that was kind of an interesting little look there. And okay, let's zoom out, see if there was anything else here. So that's in drive. I did a couple in reverse too. I don't think there's a huge difference between the signals. Now, also take a look at these signals, see how they kind of got a lot of up and down going on there because, well, the engine was running. And usually when the engine's running, you get a little bit more noise introduced in the line than you do when it's the key-on's engine off. So there's a difference there. See a lot of activity right here as it was kind of trying to recover itself back from a full throttle sweep right there. So we can see how it comes up and goes down and see how they follow each other. And then we can see our negative right there, and then it goes back over there. Just some interesting captures I think we could take a look and interpret. Right? So here's a drive test that we got that one with a shift point out of. If you look over here, it's a similar type look to the pattern over here. So this was a little full throttle run down my street, I guess you could say, going down. So you can see how it's kind of keeping it maintaining, went up a little bit on the throttle. We can see how we get a lot of activity there to close that throttle and how the throttle plate reacts. Go back over here. There's the one with the shift point, right? Going up, steady throttle. And then it shifted right there. And we can see that little shift point or blipped right before the shift point, I guess. It's where it goes. And then we can see the close. So a lot of information can be gathered with that. Now, if I'm just looking for a bad one, we can just take a look at the sweep itself. You probably want to just sweep it with the engine off so you don't get all that noise. But look for dropouts to ground. Look for glitches to ground. Just know that they're not going to react 100% accurate to each other. Right? You would think it's like a 1-to-1. I press on the accelerator, the throttle should open. Depending on the circumstances of the vehicle, if it's under load, yeah, it's going to be a lot more linear. Without a load, if I'm just testing it in the bay, key on, engine off, and I'm sweeping that throttle back and forth with the accelerator pedal, or maybe I'm even using a functional test to sweep it back and forth, that throttle plate is not going to react as well as the accelerator pedal, right? Maybe with the functional test, it might be a little more smooth. But if I'm just pressing the accelerator with no load, that throttle pedal may not react evenly to the way the accelerator pedal did because it's not under a load. Okay, so if I want more information on this, I want more information on electronic throttle controls. We can go into guided component tests. There's plenty of information and training in classes. What if I wanted a specific vehicle? Let me look up. Let me look up my car to start. So it's a 2011 Forester. So guided component test is on any Snap-on tool that has a scope. And what it is it's a database of over 5 million guided component tests for multiple different systems on a vehicle. Goes back to 1981. And as I said, it's been a while. We've had them in there for a while. It's been since 1981, as I said, over 5 million individual tests. If I go into a system, it gives me a list of components I can test, or a subsystem, in this case, throttle control system. Could do the accelerator pedal position sensor, or we could do the throttle motor. We go into throttle motor, you can see how it acts. Throttle actuator control motor, you may have heard that called a TAC motor as well, so that's another common thing. It's controlled by the ECM based on the accelerator pedal and sensor inputs. Actuator's 2 position sensors built in, main sensor, sub-sensor. There's my pinout right there. When the ECM detects trouble in the throttle circuit, idle speed will be fixed between 1200 and 1500 RPM. So you'll have a high idle after that as well. You can do a DC voltage test, and that'll check your throttle position sensor. So in this case, 0.6 to 7.2 at closed, 3.96 at wide open, and the sensor 2, 1.51 to 4.17. Also on this, we can do a frequency test. So if we wanted to look at the throttle motor positive or throttle motor negative, you could also do a frequency test and see how many times it cycles. Should see 500 hertz in that case is where it wants to be. It wants to see 500 cycles per second when we're holding it open. All right, so it just gives you a couple examples of what you might want to see. Let's go to a different car. Let's go to BMW. So we pull up the BMW, same thing, throttle control system. And then if we wanted to look at the throttle position sensor and a DC voltage test. So this will tell us where we're going to test it. And it's going to see with throttle fully closed, should be 0.5 volt to 0.7 volts. At snap should reach 4.25 volts. That's signal 1. Signal 2 should be 4.25 to 4.5 volts down to about 0.6 of a volt. So that's one of the ones that cross on the screen. So one will start high and go low. One will start low and go high. So on this BMW, that's the particular style that they use there. Component information, if you want that, it's going to tell you where it's located, best place to connect it. And then, of course, if we wanted to actually do a test, we can hit view meter. It's going to open up the meter. It's going to set the voltage range where we need it to be. It's going to set the time base where it needs to be. And then we'd be able to see it actuate on the screen. Now, I'm not connected to anything right now, but you'd be able to see it on the screen. And it sets it all up for you. Lets you know what you need to do. We look at one more here. We'll look at a Camry. Toyota, there it is. 16 Camry. 6-cylinder, sure. Okay. Engine, throttle control again. And then we have the accelerator pedal position sensor. We can do a DC voltage test there. Those are going to be pretty even with each other. Actually, those are parallel to each other. And then we see throttle motor. Information on the throttle motor. There's a lot more information there. May close the throttle a small amount to aid starting. May adjust the throttle position for cruise control, traction control, and engine speed limiting. Calculates optimal throttle valve opening in accordance with driving conditions. Uses throttle control motor to control the opening. So in this case, as we said, doesn't really care what the accelerator does. It cares what it's doing. This also helps remove small driver inputs like nervous foot to increase fuel mileage while decreasing emissions. So yet another helpful part for that. In this case, we have a couple different checks we can do. Basic check, just make sure it works. Press the throttle pedal or accelerator pedal and make sure that it opens. Resistance test, signature test. So a signature test in this case is going to be for the positive or the negative on the throttle motor. So you have your open and your close. And once again, it should be your pulse width modulation signal. So we should see a square wave there on the screen, and the duty ratio will change as the throttle position sensor changes. And then can do a resistance test on there as well. So positive and negative on the motor. We have 0.3 to 100 ohms at 68 degrees Fahrenheit. So many different tests that we can do on this. Now, another thing that you might need to do, for an example, we go to my scanner. One more thing. If I replace the throttle body on a vehicle, let's look at like a Nissan the 16 Altima. That should have it. All right, good old 6-cylinder there. And if I go into service resets and relearns on my scan tool, we should be able to see a perform an idle learn, replace or relearn the throttle body right here. So if I replace the throttle body on many vehicles, you replace the throttle body, do any repairs on it, anything like that, you usually have to do a reset. So I can go in here under relearn throttle body, and then it'll actually give me the functional reset here. I'm just going to pick an engine here, and it should give me the reset. Oh, it didn't give me the reset. I picked the wrong engine. Look at that. Idle learn procedure. There we go. Pick that engine this time. Striking out here. But you should have a reset or a relearn. It's kind of hard when you have that that simulator board on there, right? So just check. Make sure you don't need a relearn or a reset on the vehicle. We can also check in our repair information to see if we may need it there as well. So let me pop in there, 2016 Altima, and see what we have for the throttle body there. So this is Shopkey. If you have Shopkey or Mitchell, it will link automatically. If you have a Zeus or a Veris Edge, it will link automatically with the tool. It'll help you out there. So if I wanted to replace the throttle body, come in here, go down after remove and replace. And it's going to tell us how we need to, let's see, removal and installation. And then there's the different things on the throttle that we need to do. So there's accelerator, check overall functions. All right, diagnostic procedures, etc. All right, so all of that's available right at our fingertips, right from the scan tool. Makes it super, super easy. All right, so make sure you reset those throttles after you have a problem. As I said, they could have an electronic problem with the sensor, could have an electronic problem with the motor, could have a mechanical problem inside the motor with the gears that we saw, right? So you could have some wearing out of the gears in there. Just make sure you're checking all those things for any sort of problem that might be there. So with that, that's electronic throttle controls in a nutshell. And with that, that is our time here today. So make sure you tune in for new diagnostic content every week. We will be premiering a new video every Wednesday at 7 p.m. UK time. So make sure you check it out on the YouTube channel. If you're watching, well, of course, you would be watching this on YouTube, but make sure you subscribe, thumbs up, ring the little notification bell so you know anytime we post new content. And it's youtube.com/SnapOnDiagnosticsUK. With that, time for questions. If you have any questions, just feel free. Once again, if you're watching this on a premiere, just leave it in the live chat and we'll answer those. Otherwise, leave a comment under the video and we will get to those as we monitor those comments as well. So I'd like to thank you for taking a little bit of time out of your day to learning a little bit more about how you might be able to be more efficient at diagnosing vehicles using some of the information that we've given you today. Hopefully, we'll see you next week. Hopefully you can watch and see you on any of our other videos. Have a good week. Have a good night and take care.